And welcome back from the short 10-minute break. It's a pleasure to be here and to continue with Rocio's presentation where she left off. So together we've been doing quite a bit of work on regression discontinuity science for the last almost a decade now, believe it or not. And some of what we're presenting today is a summary of some of the main results that we came up with, along with some other things that we learned from other scholars along the way. And they're all summarized in this set of slides. So Rocio gave a gentle introduction to different RD designs and frameworks, and then presented quickly the idea of RD plots. And I think there is never enough emphasis in saying that those devices are extremely useful for visualization, but they can be very damaging if you try to learn something from them alone. Putting myself for a minute an econometrician hat, I should say that it's always very important to do principled estimation and inference. The RD plots are great to visualize RD designs, but they can actually be misleading in many cases. And so I'll touch base on that quite a bit for most of my presentation today. I'll try to show you how sometimes curvature of the underlying regression functions or variability of the data itself could lead to misleading conclusions, empirical conclusions, in otherwise very clean or good-looking RD designs. Great. And then she also covered the idea of local randomized experiments or local randomization in the context of RD designs. And I won't touch base on that any longer. I'll just lift a couple of ideas from that when I get to my part. And so my part is about the other approach that I think is also quite popular. And these two approaches in many ways are combined. And originally, if we were to do a history lesson, which we won't, you will recognize that these two approaches are coming together and splitting at some point from a common approach. And the common approach was all the way back. It could be found all the way back to the beginning when people were thinking about regression discontinuity science, and conceptually they were thinking of them as local randomized experiments or global even randomized experiments in some sense. And then, however, they would use arguably very parametric approaches to estimate those effects and eventually do inference on those parameters. And so these two branches of thinking about regression discontinuity science, I think both come as a response to those early approaches in the literature. The local randomization approach takes very seriously this idea of local, as if an experiment locally, and then tries to deploy ideas from analysis of experiments. And then on the other hand, the local polynomial methods come as a response to the global approaches that you would find early on in the literature. And I'll show you some examples of that as we move forward. So what is the key idea in the local polynomial approach world? Well, it is constructed from an identifying assumption, as it should be, I think. So you first think about what the parameter of interest is, and then how you can actually think of identifying it from the data. And in order to do that, you need to impose some sort of assumption, which is most likely untestable, and so it has to be believed to hold in the underlying data generating process from which we're going to try to draw inferences. And so what is the idea in this context? Well, it's a continuity one. So RD designs from a continuity perspective are interested usually in parameters that are defined at a single point on the space of the score running variable, the score variable or the running variable. And in many cases, the most popular of those parameters is the average effect. And so the more proper way to define it will be an average treatment effect at the cutoff. And that means essentially that the parameter of interest is nothing more than the difference in average responses under treatment control, under treatment status or control status for units that happen to exhibit a score value that is equal to the cutoff point. And so in itself, this may not even be called a causal parameter by some, and we can have a long and hard philosophical discussion of whether or not this can be called a causal parameter. That may depend on your views on what causality is about and how to define causal parameters. But putting that aside for today, the key part of this slide is to argue that something that is unobservable, that is based on the underlying potential outcomes, of which only one of them we can see for any one unit, depending on whether they have scores below the cutoff or above the cutoff. That difference can be represented as something based on observable data. And so the key, going from the left to the right, the second equality, is just saying that we can represent the parameter of interest as a function or functionals of observable characteristics of the underlying data generating process that, observable or estimable, at least identifiable characteristics of that underlying data generating process. And so we're going to be able to estimate these quantities. And what is the core idea? Well, the core idea is that if we're interested in the vertical jump, then we could in principle try to estimate the value of the condition expectation for the control group by estimating that regression function to the left of the cutoff, and then somehow take a limit or project it down or extrapolate it if you wish, or interpolate it depending on the values that you have in your data, but ultimately generating an estimate of the condition expectation from the left to the cutoff point. And then you will do the same from the right. You will try to estimate the regression function for the treated units, or the units who have scores above the cutoff. And then once you have a good handle on that condition expectation, then you will try to project it down or predict the value of that condition expectation at the cutoff. And so what is the core identifying assumption that is operating in the background is one of continuity. And continuity here means that in the absence of the treatment assignment rule, in the absence of the abrupt discontinuity in treatment assignment due to the RD design, you would have seen these condition expectation functions to continue in a smooth or a smooth way or continuous way, right? So what we're saying here is that in the absence of a treatment assignment due to the RD design, there should be no changes or not abrupt changes, these continuous changes in those conditional expectation functions. And if that was to be true, then we could attribute any discontinuity coming from the left and coming from the right on those conditional expectation functions to the treatment assignment, or to the treatment assigned. And so that's the core identifying assumption that will be operating in this continuity frame. So it's very different conceptually from what you would see in local randomized experiments, where the identifying assumptions not only restrict the relationship of potential outcomes with the score, but also say something about the assignment mechanism altogether. Okay, very good, awesome. So having that in place, now we can think about how to actually estimate and conduct inference on that treatment effect from a continuity or local polynomial perspective. And so in the literature, I think it is by now quite clear that global approximations are not a good idea. I think Rocio showed you this picture, which I have to show it again because it's just too cool not to show it, really. It basically says that global fits, which are actually the default in the RD plots, are certainly not the preferred method to try to infer the jump at the cutoff, right? And so the idea is I think, quite simple. What really happens is that when you try to fit a regression function using a polynomial approximation of a sufficiently high order, typically what happens is that the fit is fairly good in the center of the support, but it tends to exhibit, and this can be mathematically shown, it tends to exhibit quite a bit of variation on the tails, or in particular at the boundaries, on the support, on the compact support that you're trying to estimate. In general, that would not be a big issue, but it just happened to be the case that in the regression discontinuity designs, it is the behavior of the function at the cutoff, which is from the perspective of the estimation at the boundary, is exactly the point that we care the most about. And so from that perspective, there is a clear trade-off and a gain in this case from going from global fitting to local fitting. And so in a sense, what is RD designs, modern ways of analyzing and estimating and conducting inference on RD designs, they will unavoidably search for localization. So they will try one way or another to zoom in to a neighborhood around the cutoff, discard observations away from the cutoff, and then try to do inference using only those observations, which essentially, I believe, mimics more closely the identifying assumptions that we impose in regression discontinuity designs. We cannot really say much about the distance, the vertical distance, or any kind of difference in general for the population in an RD design, but we can say something maybe for those units that are close to the cutoff instead. And so with that in mind, in local polynomial settings, usually what you do is you search for localization, and now you have a bunch of options in the way that you can do this. And so today, what I'm going to try to talk about is basically focusing on the most common approach in the literature, because I believe it is closely related to traditional regression-based analysis in applied microeconomics, with a couple of twists that we need to take into account in order to accommodate the specificity of regression discontinuity designs. And so the way that we're going to do this is basically, we're going to propose at least to first and foremost think about localization as the core argument in the analysis. And so the way we're going to do this is by first choosing a polynomial order, which I'm going to denote by P, and that will control the degree of the polynomial that we're going to use to approximate those conditional expectations. In the example here, that P would have been 4, and this fit would have been global, and then this would have been a very, very sensitive fit near the cutoff, but perhaps a good approximation of the underlying conditional expectations in the middle between 60 and 80. And so in the context of local polynomial analysis, instead, what we're going to do is we're going to choose a lower order polynomial fit and perhaps some weighting scheme that allow us to downweight observations as they are farther away from the cutoff point in the space of the score. But regardless of the weighting scheme, perhaps there's no weighting scheme, there is just a traditional least squares regression for a polynomial of order 1 or 2, that would be linear or quadratic, say. Then the key aspect of the regression discontinuity design is that we're going to force ourselves to localize. And so localization in RD designs will be controlled by a choice of bandwidth. So in the local randomization setting, instead of age, we use the notation of little w, just to mimic the edges of the window where the local randomization assumption was believed to give a good approximation to the underlying data generating process. In the context of local polynomials, we're going to use the letter h that determines, again, the distance from the cutoff that defines the region where we're going to conduct estimation and inference. And so the way that the procedure typically works is you choose the desired order of the polynomial, you choose some weighting scheme, sometimes it's called a kernel, and given these two characteristics, then you go ahead and choose a bandwidth that purposely discards a lot of observations and zooms into a nearby region of the cutoff point. And so there are different ways of choosing this bandwidth. I'm going to discuss 2 of them and their corresponding optimality properties. So as everything in econometrics and possibly in life, there is no one global optima. So everything is relative to what your beliefs are. Or in this case, in econometrics or statistics, we typically define it in terms of a risk function or a loss function. So at the end of the day, we have to set the rules of the game. You need to define what we care about. And once we care about something, we might be able to obtain an optimal choice. In general, there is no optimality that is uniformly true for everything. It's all relative to what you deem to be important for your problem. And so in the context of bandwidth selection, there are 2 criteria that I believe are particularly useful to think about how to select that bandwidth. One refers to a point estimation criteria, i.e. we're trying to find a bandwidth that gives us the best possible guess of what the treatment effect is in a very special sense. And the sense here will be mean square error. So for those of you who may not remember what that is just something about how good a point estimator is as metrized by the expected square difference between the point estimator and the actual target parameter, in our case, the vertical jump at a point, or the cutoff point. And so the mean square error essentially trades off bias and variance in a particular way. And so a second way of choosing the bandwidth that I'm going to talk about briefly is related to inference properties. So one could say, hold on a minute, I'm not particularly interested in developing an optimal point estimator for the RD treatment effect, although arguably that is a major goal in practice, but also I may want to ask a question, how should I choose the bandwidth if I wanted to have the best possible Gaussian or distributional approximation in order to conduct inference? And one way to answer that question is by looking at the errors that you make, but not in terms of mean square error for point estimation, but in terms of discrepancies between the sampling distribution of your statistic, typically a t-test of sorts, and its limiting distribution. And of course, as anything in life, very few things are Gaussian, but many things are called to be close to be Gaussian. And so we can metrize or characterize the discrepancy between the sampling variability or the sampling distribution, more precisely, of the statistic and its target limiting distribution, the normal distribution. And so those errors can be characterized, and not surprisingly, will also be a function of the bandwidth. And they will be a function of the bandwidth in a different way. And so you will trade off those errors in a different way, and eventually you will get a different optimal way of choosing the bandwidth. And there are many other ways to do this. Okay, great. So I'll touch base on that briefly and show you in practice how things change when you decide how to choose your bandwidth. And what are the drawbacks of shifting this as well? Once you do that, you're ready to go because you know the polynomial order, you know the weighting scheme that you decided to use, and now you can go straight ahead and choose the bandwidth. And once you have that neighborhood selected, you are ready to construct your point estimator. So again, the point estimator will estimate the regression from the left, the regression from the right, and then it will construct that jump. And that will be the point estimator that we're going to call the RD treatment effect. And then once we do that, now we have to decide how we're going to conduct inference, and hopefully we would like to use a procedure to form confidence intervals or perhaps conduct hypothesis tests that are procedures that are valid from some objective and demonstrable way. And so I'll talk about a couple of ways to do that, but they're all going to be related to an idea that Rocio and I and some of my close and amazing collaborators have put forward over the years, which is the idea of robust bias correction. And so I'll talk a little bit about how this idea comes about and why we think is a useful way of trying to understand or characterize better issues related to invalid inference that otherwise will come out if you were to apply the naive or the simplistic approaches that sometimes are seen in practice. And so I'll talk about that as I get there. Okay, so let me try to ground this idea. So now I'll go a little bit quicker so I can get to the meat of the analysis. So as I said before, we're trying to approximate regression functions from the control side and the treatment side locally. So to ground ideas, think of the most prototypical case. I would argue it should be the default in most applications. Every time I get to review a lot of RD papers, better or worse, and many of them are applied. And whenever I see that the linear fit has been excluded, I typically worry a little bit. I'm not saying that you should always use this, that you should only use this, but certainly a linear approximation is arguably a very safe first step in the analysis. And then how do you do this? Well, you choose p equal to 1, and then you select a window by choosing a bandwidth h, such that all the units to the left of the cutoff, but up to that value h, is they are in the control group, and then all the units to the right are in the treatment group. Okay, and so we're going to split that and we're going to analyze them separately from the left and from the right. And in each case, we're going to just run a least squares regression. So we're going to run a least squares regression, a weighted least squares regression from the left, and a weighted least squares regression from the right. And so here, the weights are just going to try to capture this idea that observations closer to the cutoff provide arguably more identifying assumption, whatever that means, but certainly we would like to upweight them. And then observations farther away from the cutoff, but still in the region of analysis determined by the bandwidth, they will receive relatively less weight. And so sometimes we like that idea. And so in order to do so, we can choose different weighting schemes that one could use. And so there are three of them that are quite popular in practice. And the three are plotted here. And they are arguably the most interesting ones. So the first one, which is a default from a point estimation perspective, because of its optimality properties, which is not super important today, is known as the triangular kernel. So this kernel is a weighting scheme that downweights observations as they are placed away from the cutoff in terms of their score. They are downweighted linearly, right? So you can also downweight them quadratically, and that is typically called the Epanechnikov kernel. Or we may choose not to weight or downweight observations at all, and that is typically called the uniform kernel. So the uniform kernel is going to resemble a traditional least squares regression. Whenever you use the uniform kernel, you are not weighting or downweighting or upweighting observations, all get the equal weight. All we are really doing is localizing, dropping the observations outside the neighborhood determined by the bandwidth, and literally running a least squares regression. And so you can, of course, run two least squares regressions, one from the left, one from the right, or you could also package all together in a single least squares regression. And the single least squares regression will simply define a dummy variable for whether or not units are above the cutoff, and then you will interact that dummy variable with the score. In this case, keep in mind, you should also weight by the weighting scheme, if there is such a weighting scheme, unless you choose a uniform kernel. And then, of course, this representation is only valid for p equal to 1. If you were to think of quadratic fitting locally, then you will still localize this way, but then you will have to add the quadratic square term and the interactions as well. Okay, very good. So once you chose those ingredients, we are ready to explain how the procedure works. I think it's fairly straightforward, so I'm going to go fairly quick. Imagine this is the true data generating process. Notice that there is a condition expectation to the left, there is a condition expectation to the right. In fact, they are continuous at the cutoff in this data generating process that we created. And importantly, they are not parallel, right? So that's something that is kind of important too. RD designs are going to give us something about what happens there at the cutoff point from a continuity perspective, or perhaps something around here if we are willing and able to apply a local randomization analysis. But certainly it will be hard to learn something about down there, right? So the power of the idea, the identification power of regression discontinuity designs is naturally local to the cutoff. And so anything that you aim to say or do beyond that point, we're going to deem, or the literature deems, as extrapolation, which has a natural analog to external validity, if you wish, in the context of randomized experiments. And so RD designs are going to have high internal validity. They're going to give us a lot of information about what happens near the cutoff, but very or no information about what happens outside that region in the absence of additional assumptions. And there are quite a few different approaches out there, which I don't think today I'll have the time to touch base on. But there will be references at the end and some review articles that we are writing at the moment that will touch base on those ideas as well. Okay, great. So getting back to this, this is the regression discontinuity setting. And so this is the true underlying model, but we don't get to see that. What we get to see is data. The data in this case is plotted in red for those above the cutoff, in blue for those below. And of course, here I'm putting together the true underlying conditional expectation functions as well as the data. In reality, you don't even see that. What you really see is the data. And this is a very clean, escalated example where the data is clearly separated from above and below according to the groups. In reality, this data will never be as nice as that. So just to give you an example, imagine that I wanted to plot for you the Lewis and Miller data, which is such a fantastic paper and data set for us to try crazy things on. So far, we haven't been able to break it, although we keep trying. And here is the RD plot that you will get if you were to get a bunch of beans, which effectively says plot each data as an individual dot. Right? So if we put 1,000 beans on each side, essentially each bean will contain 1 or 2 observations, maybe even less. And so this is basically a scatter plot. And now you can see that there is no clean separation as you would have hoped to see in my stylized example. Nonetheless, the question remains, is there a treatment effect, formally speaking, that we can estimate and later attach uncertainty to? Okay, great. So here's the data set in the stylized world. So how does local polynomial methods, how do local polynomial methods work? Well, as I told you before, you choose a bandwidth. The bandwidth localizes, immediately removes all that data. That's gone for us. And now we're going to do the analysis only using the data inside the bandwidth region. And then the way we do it is quite simple. We run a local, perhaps, a weighted least squares regression of some power p, in this case p equal to 1 is linear, and then we predict the value at the cutoff. And then we do the same from the left, and then we predict the value at the cutoff. And so here, let me pause for a minute, and again, RT designs are fundamentally identified in the limit, and therefore there is an extrapolation component that is unavoidable. In other words, at most, and typically never, you will see observations exactly at the cutoff. So you will only be able to estimate the regression functions with observations that are slightly away from the cutoff. Maybe the first observation landed right there, then right here, then here, then here. In the particular application of Lewis and Miller, by construction, there is one and only one observation at the cutoff, which is the 300th municipality that determine the cutoff itself. But other than that, all other observations are away from that point. And so it's unavoidable that we're going to estimate using data that is around here and here. And then we're going to predict essentially to the boundary of the support. And so we can digress quite a bit about whether this is extrapolation or not, and what exactly identification means in this case. This is something that we do quite commonly even in statistics or econometrics when you think about estimating functions at boundary points. If the variable, the conditioning variable is continuous, then the probability of seeing any one observation at the boundary will be 0, and in practice you will never have those observations there. So there's always a tiny little bit of extrapolation that is going on underlying any regression discontinuity design. And with that comes bias. So bias tends to be a big problem because usually you try to predict what the conditional expectation is at that point, but of course your linear approximation only does so much of a good job because it's an approximation to the true underlying conditional expectation. And so in these examples, you can see that the predicted value differs from the actual population conditional expectation value. And this vertical distance here is what we would call the bias, or the final sample bias. I mean, of course, bias is defined in terms of expectation. So at the end, this is just one realization, but the idea is the same. So essentially, there will be a vertical distance that captures this difference. And we're going to refer to this as misspecification error. It's natural, right? So we go near the cutoff, we define a region, and then we postulate that a linear regression is a good enough approximation for this underlying unknown conditional expectation that needs not to be linear at all. And so the question is, how much of a mistake are we making, right? And so intuitively, you can imagine that if you were to choose a large bandwidth and the conditional expectation exhibited enough curvature, then the linear approximation could not do a good job. right? So in this example, for instance, the condition expectation looks like this and like this. And then because the bandwidth is quote unquote large, whatever that means, the bottom line is that you see that the linear fit would not do such a good job. If we were to shrink the bandwidth, then we would be approximating what is, by assumption, a continuous function, by identifying assumption. And therefore, in a local neighborhood, more local than H2, we would be able to do a better job. And so that's exactly the idea, right? So if we were to shrink from H2 to H1, then all of a sudden the same linear model could do arguably a better job, hopefully a better job, under some assumptions. And so this change in bias from a large bandwidth to a small bandwidth is going to play an important role in the analysis. I mean, ultimately, our methods are going to be, all models are fundamentally misspecified, and so the question is how we think about misspecification and what we do about it. And so in the context of bandwidth selection, this is very clear. If the only goal was to reduce misspecification, we would just shrink the bandwidth as much as we can. Of course, in practice, that is a naive response to the problem, because the smaller the bandwidth, the less observations we have to do the estimation. And so the price that we pay for reducing misspecification errors naturally is larger variability and eventually inability to estimate the function at all. And so we need to trade off these two. And that's where the trade-off comes in to select the bandwidth. So we can select bandwidth based on a criteria. For example, for point estimation, that would be the idea of mean square error. And in mean square error settings, we're going to be trading off bias and variance and finding the optimal sweet spot where that bandwidth lands that give us the best trade-off between bias square and variance. And the idea here is very simple. I'll just show you a picture about it. If you choose a very small bandwidth, bias is very small, but variance is too large, we're better off by slightly increasing the bandwidth and improving on the trade-off. And then as I keep increasing the bandwidth, I'll reach my optima. And as soon as I cross that point, again, the trade-off flips and continues up, right? So the mean square error is a beautiful convex objective function that you can solve for, and under some conditions and assumptions, you can even give a fairly good characterizations of how this choice looks like. So in the case of a local polynomial regression, the choice would look like a fraction of the sample size, in particular a power of the sample size, times a constant. And the constant needs to be estimated. The estimation requires some additional steps, which are not super important for the purpose of today, but then eventually you can construct an estimator of that bandwidth. And that will be the default in the analysis. So typically you choose the bandwidth by fitting these constants and then selecting the bandwidth in a data-driven way. And that's very important, right? Because data-driven procedures take a little bit of the discretionary from the researcher away, so they reduce p-hacking, they increase transparency, and they allow for something that is fully replicable. So you don't need to start asking questions like, why do you choose a bandwidth of 5 or 10 or 15? We can start thinking about, okay, what the data is telling you about what the bandwidth should be. And of course, there is no unique bandwidth. So here I put a second bandwidth out there. This bandwidth is different. It has a different rate of convergence, i.e. a different fraction of the sample size or power of the sample size is being used. And more importantly, a different trade-off between bias and variance is being done. So in this coverage error approach, which effectively targets the best possible distributional approximation of the t-statistic distribution, sampling distribution to the Gaussian distribution in the sense of coverage error, these two are minimized, their distance is minimized by this particular choice. And here you can see that instead of trading off bias square and variance, what you trade off is bias and variance. And so again, there is no right answer. You just need to choose what you think is best for the problem at hand. Typically the default will be to construct a point estimator that is optimal in a mean square error sense, and that will be your starting point. So many people in practice, and I would argue it's a good idea, they decide on a bandwidth for point estimation, and then they would like to keep that bandwidth fixed. Part of the reason is because then they're using the same observations both for point estimation and uncertainty quantification. The only difference is how to use them. And so that will be the procedure, at the heart of the procedure I will discuss in a few minutes, okay? So there are a couple of ways of doing this. I told you all this before. In practice, you're gonna put hats on these things. So as you know, econometricians love to put hats on stuff, and that's kind of our job. So we just put hats on things whenever we don't know them. That means you go to the data and you get your best guess of those, and then you plug them in and you go with that. Okay, awesome. So once you have these ingredients, we're ready to go. So how we're gonna do inference here? Well, I hope it's pretty straightforward. Once you decided on how to estimate this point and this point, and notice this is just a least squares problem. So we all know our least squares very well. So we could very easily rely on traditional least squares inference to try to learn about the uncertainty on our point estimators, right? And so the typical approach here would be to form a t-test, right? A difference in means, but for the regression intercepts. And then that will put the two intercepts, which will be the treatment effect, the point estimator for the treatment effect, the vertical distance estimated, and then you will put down here the standard error of the difference. And so to the extent that this behaves like, and it does, a two-sample problem, then the variance of a difference is the sum of the variances, and so you can just plug in your preferred Eicher-White, robust, cluster robust, or whatever version you like to estimate the variance of the intercept from the left, the variance of the intercept from the right. You plug them in, and you get yourself a great t-test statistic. And then comes the hope. The hope is that whenever you do that, that t-test statistic behaves like we know traditional least squares models or least squares problems behave. That is, the t-test enjoys a distributional approximation, which is a normal 0-1. And so if we get that, we are in business, right? And that will be what you typically appeal to every time that you use reg in Stata or LM in R. What you do is basically you postulate a linear regression model, you assume it's correctly specified, then you appeal to either finite sample or large sample distributional features, and then you just form your preferred confidence interval, which is point estimator plus minus, say, 2 times standard errors. And that would be the 95% typical confidence interval. What's the problem here? Well, the problem is one of misspecification error, right? So as I told you before, the key distinctive feature between regression discontinuity designs and traditional least squares problems would be that in regression discontinuity designs, we know that we're misspecified. Furthermore, we take advantage of the misspecification in order to construct an optimal bandwidth choice. So if you remember correctly, I said, oh, the bandwidth choice is a ratio of variance to bias. But of course, if bias was 0, then there will be no choice other than infinity. Therefore, the bandwidth will be the entire region. That makes sense, because if the model is truly linear, why would you localize at all? In practice, we don't like that. In practice, we do localize. We don't believe the regression function is linear, and therefore, we are facing a natural trade-off. If we're going to choose the bandwidth, the bias cannot be 0, but if the bias is not 0, then in general, the distribution approximation is not correct, because it's not centered at 0 in general. It depends on the choice of bandwidth that you decide to use. And in particular, if you were to use the mean square error choice, then you will discover that the limiting distribution exhibits a first order bias. And that postulates a challenge. Now we need to account for that bias if we want to go ahead and conduct inference. We cannot just rely on 1.96 quantiles and go ahead and use least squares methods. We cannot simultaneously choose a bandwidth for mean square error optimality and then pretend that there is no bias. We need to choose one. Either we choose the bandwidth in some other way, or we account for the bias afterwards. And so in the proposal that we typically use and recommend, what we do is essentially to provide a bias correction that comes about for controlling for that extra misspecification error that you introduce when you use the mean square error bandwidth. And then because this misspecification error has to be estimated somehow, so you need to actually adjust the location of the confidence intervals by relocating them. Their centering being relocated to a point where this bias is no longer the first order present, then that induces additional variability. And that additional variability can be accounted for. And so the procedure that we recommend and having our software implemented, typically what it does, it adjusts the location of the confidence interval and then accordingly enlarges the intervals by adding an account or trying to account for the extra variability that the bias correction estimate introduced in the first place. And so at the end of the day, the procedure will shift confidence intervals in location and in scale, right? So these confidence intervals will typically be displaced in their location and they will be enlarged by this additional variability introduced in the scale. And that doesn't mean that the confidence intervals will lead systematically to less statistical significant results, for example, because it all depends on the trade-off of the displacement to the enlargement of confidence intervals. So let me show you a couple of examples on how this works. So this picture tries to capture the idea of different possible bandwidth choices, and in particular, the mean square error optimal will lead to least squares confidence interval that by construction will have a first order bias. This is a mathematical fact. I don't think it's up for discussion in general. Of course, it can happen to be that that particular bias constant is zero at that point, in which case this would have not been well defined to begin with, other than infinity, of course. So once you have that, there is a bias that leads to over-rejection of the null hypothesis. So in practice, we will see that choosing the optimal mean square error bandwidth for point estimation in RT, and then constructing confidence intervals using least squares ideas will lead in general to misspecification in the location of the confidence intervals and over-rejection of the null hypothesis. So that means that we're going to be over-rejecting the null hypothesis of no treatment effect. And a back-of-envelope calculation tells you that the coverage that those confidence intervals will have will be roughly 82% for a 95% nominal level confidence interval. That means you're going to be rejecting roughly 10% of the time incorrectly the null hypothesis. So how do we fix that? Well, as I told you, we can recenter the confidence intervals, but then we need to enlarge them appropriately, okay? And so that's kind of the idea. And this problem might or might not be more important as you move yourself in the scale of bandwidth. If you choose a large bandwidth, large relative to the mean square error 1, then the problem will be exacerbated. More bias will kick in and further the distance in the centering of the confidence interval from the true nominal, the true population centering. If you go to the left of the mean square error, something that is called undersmoothing, then you can mitigate this problem. So you reduce the bandwidth relative to the mean square error, and eventually, if you reduce it enough, you might be able to regain nominal levels, theoretical, in large sample nominal levels that have been postulated. Of course, that implies a loss of power. So typically, as you do that, you can see the confidence length, the length of the confidence intervals become to larger and larger, and that is mechanical again, because the bandwidth is shrinking, less observations are available, the variance is larger, and the confidence intervals explode. Okay, great. So let me now show you this in action for 5 minutes, because I think it's cool to see how all these ideas come about. And so what I'm going to do is I'm going to try to go back to the original paper of Luger and Miller and try to replicate these results. And in particular, one thing that I love to do always when I see these papers is to say, well, in these papers, they chose a bandwidth of 9, 18, and 36. Of course, they are not to blame. They did that back in 2004. We didn't have all the theory and ideas that we have today, but nonetheless, it would be cool to ask the question, what is 9 relative to the mean square error bandwidth that you would like, you would obtain nowadays? And so we can do that. And so let me just show you an example of what that would look like. If I can find it, of course, maybe down here. Oh, there we go, beautiful. So the typical example would be like this. So this will be a plain vanilla estimate for the Luger and Miller data. So on the left-hand side, you have 2,400 observations. On the left, you have about 300. There is a few missing data values points there. And then the conventional here is nothing more than these pinky intervals and procedures, right? So it's a least squares approach to this problem. And then there, you see now that you have a point estimate. And because this is chosen to be mean square error optimal, that means that this point estimate is a mean square error point estimate of the RD treatment effect. Associated with it, you can construct a confidence standard error. The standard error is the straightforward least squares variance standard error. In this case, it's an Eicher-White heteroscedastic robust estimator. And then we have two options. We can do inference based on the least squares approach. That is the one that assumes no bias, which again, it would be inconsistent with the idea of choosing a mean square error bandwidth in the first place, but nonetheless, you can do that, I guess. And then alternatively, you can actually control for the bias correct, and then enlarge confidence intervals accordingly. And so that will be the confidence interval that comes out down here. And in this example, for instance, the p-value actually decreases. It goes from 0.046 to 0.42. That essentially means that the shifting of the confidence interval away from 0 is more than proportional, quotes unquote, depending on the distribution, relative to the enlargement of the scale. And so in this case, the p-value actually goes down. So it's not even true, of course, that by doing this robust approach, you automatically lose significance. It really depends on the application at hand. And now, more importantly, what is 9? So as I said before, they use this 9 here. So, and they use 527 observations, right here. So what is 9 for them? And let's check. Well, here the optimal bandwidth is actually almost 7. So they are already a little bit over smooth. They have a bandwidth that is larger than the optimal bandwidth. And then that means in the picture here that if this is 7, then they're about 9. They're about there. Right? So in this example, they are a little bit away and farther out from what it would have been the optimal mean square error bandwidth in the region where the bias of misspecification error is even larger than you would expect to see. And so that's okay, that's what it is. And so we can actually replicate their results. So we could actually use 9 as they did. And so here's an example where we can just mechanically choose a bandwidth of 9 and then see what the results would look like. And now you can see that with a bandwidth of 9, the coefficient, the point estimator actually is decreased by about 10 to 15%. And that may be arguably potentially due to these misspecification errors with too large bandwidth to approximate correctly the condition expectation near the cutoff. And so, in particular, if you want to replicate their results, you will see that their result actually is a minus 1.895. In order to do that, they actually use a uniform kernel because back in the day, they were using least squares regressions with no weighting. So instead of using a triangular kernel, what they did is they did a uniform kernel. So here is the replication for them with the uniform kernel, and now you get exactly the minus 1.8952, which is the result reported in the QJ. And then there is some issue with the standard errors, which in the interest of time, I'm not gonna touch base on today, but if you explore the code, you can play with it and get a sense of how that works. Okay, cool. So that's a short replication of that in the interest of time. And now in the last minute or two, since I started 2 minutes late, I earned my 2 minutes. I'm gonna mention quickly ideas of falsification and validation. I know I'm not gonna be able to cover everything here, and I knew that coming in, so I just gave you one slide of this. And the slide basically is just a reminder that regression discontinuity in science, to me at least, and one of the reasons I really liked them when I started working on them was that they were particularly good at falsifying, verifying, validating, interpreting. They have a bunch of interesting features that are unique and not necessarily portable to other observational studies methods. And in particular here I mentioned a few. So there is a very interesting way of thinking about whether there is manipulation of the units near the cutoff, right? So underlying the idea of continuity or the idea of local randomization, there is this notion that units should not be able to systematically place themselves in one treatment group or a control group by their choice. In other words, if they could systematically place their scores above the cutoff or below the cutoff, then obviously the comparability will no longer be there. And intuitively, you would expect them to be quite different between treatment and control groups. And so this idea was originally posed by more practitioners, and then later it was formalized and investigated in different ways. And so there is a very popular test, which is called the density continuity test, was proposed by Justin McCrary. And that one in particular seeks to try to check whether there is a disproportional jump in the mass of units on one side of the cutoff or the other. And so there are different ways of doing that. I'll show you a very quickly one visually because I think it's kind of cool to see. They just basically estimate the density of the score variable from the right and from the left, and they hope to see that there is no discrepancies, no surprises in terms of the number of units on either side of that cutoff. You can also look at the same idea from a binomial assignment test perspective. And so this code immediately tells you p-values for how surprising it is to see different number of units on each side of the cutoff. And then you can see very quickly the p-values are way away from any significant levels. That means that the number of observations expected to be seen on each side of the cutoff for different regions around the cutoff are roughly what you would expect to see if you were to randomly assign them. And that kind of appeals to the idea that they are not systematically placed on one side or the other. Of course, this is neither necessary nor sufficient. They could be placing themselves one side or the other, but they will do it in such a way that they're compensating the counts. And so this is just a very nice heuristic way of thinking about the problem. And then here's a list of many other ways of falsifying and investigating the validity of the design. I won't be able to touch on all of them. Let me just mention that pre-intervention covariates is a great idea. This was proposed by several people, including Lewitt and Miller. They have a great second table that I did not put here, where they check whether the treatment has any effect on outcomes or pre-intervention covariates that are deemed to not be affected by the treatment. And so that's a great check that indeed the channel of the treatment effect is coming from to the outcome that we care about and not other outcomes or pre-intervention covariates. There are many other tests that you can do. Good. So I'll stop here for the interest of time. So let me just thank not only on my behalf, but also on Rocio's, since we are sharing the slides to begin with. And let me just mention that in this website here, if you were to go there, you can actually find all kind of references that for all the stuff that we discussed today.